Hello everyone, this is lecture 39 of PEC. Let's discuss nonlinear resistors. In this week's lessons, we will introduce you the analysis method for the circuits containing nonlinear resistors. I've always said that only by knowing the nonlinear resistors you can truly understand the linear resistors. That is to say, by comparing, we can know their respective substantive characteristics. Well, let's start from learning the differences between the linear and nonlinear resistors. The figure is a standard linear resistor. In the case of the associated reference directions of U and I, we know its characteristic curve in the UI plane. It's a straight line crossing the origin. The angle between the straight line and the horizontal axis, that is I-axis, is alpha. Tangent alpha is equal to the resistance of the resistor. This is the main content we've discussed previously. As to the so-called nonlinear resistor, its circuit symbol ends a line compared to the linear resistor. What's about its UI characteristic? You can't write out U equals R times I directly, otherwise U and I have the linear relationship. We often write it in the way that U is the algebraic function of I, or I is a function of U. Even sometimes it is written as U and I has an implicit algebraic function. But I want to emphasize 2 points. The first point is that U and I have the algebraic relationship. The second point is that I should be equal to 0 when U equals 0. These two conditions are fundamental characteristics of these three expressions for nonlinear resistors. We have given some mathematical expressions of the nonlinear resistors just now. Now let's look at the three examples of the nonlinear resistors. The first example is a tunnel diode. Its UI features in the first quadrant is like this. First of all, I need to point out in the nonlinear resistive circuits, we often choose the voltage as the horizontal axis and the current as the vertical axis. You must be accustomed to it gradually. Let's look at this curve. For such a curve, you can find that when the voltage is given as any value, the current has a unique corresponding value. But it is not necessarily true in return. When the current is a certain value, there may be different corresponding values of the voltage. For this circuit, we can write it as a form of I equals A0 times U plus A1 times U squared plus A2 times U to the power of 3. We usually call this kind of resistors as a voltage-controlled type. It means that every voltage corresponds to only one current. In the UI plane, where the horizontal axis is for the voltage and the vertical axis is for the current, the UI features of this resistor looks very like an English letter N, so we call it the N-form resistor. Obviously, the existence of the N-form resistors hints the S-form resistors. You see, for the gas-filled diode in the UI plane, where the horizontal axis is for the voltage and the vertical axis is for the current, its UI features in the first quadrant looks like an English letter S, so it's called the S-form resistor. Similarly, for each current, there's only one corresponding voltage, but for each voltage, there may be multiple corresponding currents. So we write its UI relationship as this form. It's an expression of the third power of current. Now, we know the reason what we learned in previous page, that sometimes it is suitable for expressing the current with the voltage and sometimes expressing the voltage with the current. That's because UI features are different for the various nonlinear resistors. The third one is a common diode. It's also called as a rectifier diode. Its expressions can be written as this form. In condition of the reference direction of U and I, this is current. This is voltage. U, TH, and IS are the characteristic parameters of the diode. Drawing the equation in the UI plane, it's an exponential curve crossing the origin. You can find that when U is very small, the value tends to be 0, so the line tends to be minus IS. The IS is usually called as a reverse saturation current. Its magnitude is about 10 to the power of minus 12 ampere. UTH is about 10 millivolts. Because after through the origin, the current increases exponentially with the voltage. So we call this section the conductive section. When U is less than 0, the current is about 10 to the power of minus 12 ampere. That is order of p ampere magnitude. So we call it the cutoff section. In brief, a diode can be roughly divided into the conductive section and the cutoff section. In the next few lectures, there will be more in-depth analysis for the diode. By dividing its conductive section into several segments for analysis about the diode, we give a simulation now. Through the simulation, we study the characteristic curve of the voltage and current of the diode. The two terminals of the diode are applied with the voltage source V1. We measure the current of the diode. Click Simulate Analysis DC Sweep. The current source V1 from 0.5 volt to 0.75 volts by sampling every 0.01 volt. The output is minus IV1. Click Simulate. Choose white background. The horizontal axis is the voltage across the diode, and the vertical axis is the current flowing through the diode. The current is very small and close to zero at the very beginning, about minus 10 microamperes, which can be regarded as no conduction. As the voltage increases, the current is zero when the voltage is 0 volt. As the voltage continues to increase, the current is with the order of milliampere amplitude when the voltage is about 400 millivolts. Then, as the voltage increases, the current increases rapidly. Simulation results show that the characteristic curve of the voltage and current of the diode meets the exponential variation law.